Hi and welcome. I'm trying to learn particle physics and today the standard model. And after we've done that, we're going to do a lunge training. And if you participate in the lunge training, in the second half of the video, which will be exercises in lunge and in squat position, isometric exercises, that's at your own risk. Now, the creation of a standard model. In the 1970s, the theories describing the electromagnetic and weak and strong nuclear forces were brought together in a loose association known as the Standard Model of Particle Physics. I'm going to read that sentence again. In the 1970s, the theories describing the electromagnetic and weak and strong nuclear forces were brought together in a loose association known as the Standard Model of Particle Physics. So the Standard Model of Particle Physics is a description or a bunch of theories about the electromagnetic force, the weak force, and the strong nuclear force. So there are different types of forces. Electromagnetic force, let's just say this is part one. These are magnets. They are somehow pulling to each other. It's part one, it's just the basics. And the weak force and the strong nuclear force. And they are somehow having forces. They can pull on each other. And there are theories about how they're doing that. And the Standard Model of Particle Physics brings them together in a loose association. It has been a widely successful construct, while being also manifestly flawed. That sentence seems to mean that it was a very good standard model, that it works well, but that it has flaws, that it has problems in it. The name Standard Model was a considered understatement, says theorist Steven Weinberg at the University of Texas at Austin, who coined the term in 1974. Now we want to understand it all. So there is a university in Texas and Austin in the United States. In the United States there's Texas, that is more the south, and there's been the city Austin, and there's a university, and that university there was, or is, Steven Weinberg. And Steven Weinberg said once about the Standard Model that it was a considered understatement, so that the person who said it intentionally tried to use a name which understates what it is. He then says, "I didn't want it to become a dogma, but more a basis for conversation and experiment that might lead to the discovery that it is wrong." Okay, that means he put something forward so that the people can't wait until they know something else and get it then right directly. A bit like I just did it with just claiming that electromagnetic force works like magnets. I have no idea if that's true, but now for claiming it and bringing it forward, maybe it happens that it didn't want it to become a dogma, but more a basis for conversation and experiment that might lead to the discovery that it is wrong. And at least we come to the point. If we now already don't understand what electromagnetic force is, we're not going to go forward. So we're just going to say it works like magnets. Two magnets can pull to each other. So now we can proceed forward. Otherwise we would maybe just stop. We just don't know what electromagnetic force is. We're just going to say it's like magnets. As a basis for conversation and experiment, so that we might find out what is wrong about it, or that it is wrong. And that is what Steven Weinberg said about the Standard Model. And that is loose bringing together of theories about how the electromagnetic, the weak and the strong nuclear force works. Its basics can be written on a postcard. So the basics of it can be written down in 5-6 lines. There are the fermions, the particles that make up matter. Okay, they're fermions, they're just called like that. And they make up matter. We're just going to say that book is matter. I think that book is matter, actually. And there are different types of things. Now, this paper here is purple, this is white, so there are different types of elements. Colors, whatever, however they happen to be. And one type of whatever, if we're making it blue or whatever color it is, or white, there are hundreds of different colors, so why should there not be somewhere something called fermions? And these fermions make up the matter. These consist of 6 quarks arranged in pairs to make 3 generations, identical in all but mass. No, it starts to get complicated. There are 6 quarks. We're just going to say that there's something else, like fermions. We know there's white paper and white color and blue color and gray color. There are fermions. Maybe fermions are blue. And now there are quarks. Okay, and there are 6 of them. Why not 6? and they are arranged in pairs to make 3. 6, so they are 2, 2 and 2, not to make 3. So they are 3 and 3. In pairs to make 3. So they are 3 and 3. Okay, why not? A book has also left and right. So why should there not be pairs of quarks? One element, whatever it is, and another one. And why should there not be 3? 6 of them. Such as electrons and neutrons. In a way, that book is also, I think that is, I know actually that is the double length of it. No, that is the potence of it. So why should it not be ordered like 3 and 2? Makes sense. Whatever. There are 6 quarks. We try to imagine it, and if not, we're bringing something forward for conversation, experiment, just to prove that it is wrong. No, they are arranged in pairs, and they make it in 3 generations. They just called like that. It's also written here in this quotation marks. We're just going to say that these are generations. There's generations 1, 2, and 3. But these are just 2 pairs with each of 3 of them, so they are 1, 2, 3. Whatever. It's not that important. The main thing is that we understand it. Let's look how far we can go with that approach. Identical in all but mass. Okay, these 6 things are identical, but not in mass. So they have the same color. We're just going to proclaim the same color, the same shape, the same size, everything the same, but not the same mass. So one of them is heavy, one of them not. One of them not. So like an iron bowl, what do they call it? An iron football and an air-filled football. They're having the same size, but one is not to play football with. And there are also 6 leptons. We're just going to say they are fermions, they are quarks, and they are leptons, such as electrons and neutrinos, and they are arranged similarly. Okay, there are 6 leptons. We're going to say they're all 2, 2 and 2, or 3 and 3. We don't know yet. And there are also electrons. We're saying they're also 2, 2 and 2, and neutrinos 2, 2 and 2. Why not? There are 100 different types of trees, 100 different types of colors. There are fermions, quarks. Somehow they have to all come about with their different types of things. Something makes this, whatever color it is, this green gray, this makes it the white, or maybe it's nothing in it, and that makes something this purple. So they are quarks, fermions, electrons, neutrinos, and they are all ordered like 3 and 3 or 3, 3, 3. There are also a handful of bosons, like the photons that transmit nature's fundamental forces between the fermions. They're having a diagram. First we try to understand it, maybe already the diagram proves us false. There are a handful of bosons. Okay, another type of thing. Like the photons that transmit nature's fundamental force between the fermions. Photons. They are transmitting the natural fundamental forces between the fermions. Okay, we have the fermions. And these fermions are the particles that are the matter. And there are 6. These fermions consist of 6 quarks and 6 leptons and electrons and neutrinos. Okay, fermions are something bigger. And in them there are 6 quarks, 6 electrons, 6 neutrinos, and 6 leptons. And also a bunch of bosons. And photons seems to be a type of bosons. Why not? The Yorkshire Terrier is a type of dog. So why should there be not a type of bosons? And photons seem to be a type of bosons. Photons, whatever they are, and they are bringing stuff between the fermions back and forth. And these fermions are these bigger things in which these 6 quarks, 6 electrons, 6 neutrinos, and 6 quarks are. And now between them, there are all the bosons. And they're bringing from fermion to fermion. See diagram page 14. We're going to do that. But first, let's take it really good. We're having these fermions. And, no, are these fermions already? I need a bookmark. I don't want to see it. Not yet. Yes, okay, there are fermions, like cells. And in them there are 6 quarks, and 6 electrons, 6 neutrinos. And then there's another fermion, and the bosons are running as messenger from back to forth and transmitting natural forces. Now to page 14. Is it bad? Diagram page 40. The Standard Model. Our best understanding of the building blocks of matter and the forces that glue them together. We have these quarks. Oh, I get it. Up and down and down, straight and top and bottom. And they have also these names. Up seems to be in U, down a D, charm a C, and S. These are just a bunch of things in the letters. Leptons. And they're electron, muon, and tau. Electron, neutrino, muon, neutrino, tau, neutrino. Okay, they're just ordered a bit. And some of them have the same size but different mass. There's something differently. And the other ones are the bosons, and they are the force carriers, the photon, the VNZ, a weak nuclear gluon, strong nuclear mass giver. We're going to stay with what we have. There are 6 of these quarks, 6 of these leptons, a bunch of bosons, and they seem to be not part of it, and we're staying with the text. We're going to use that as a way to learn the names, because it seems to be that this makes up all the matter, or much of matter, and it makes sense to have a name for each of them. Let's read it fast again. There are the fermions, the particles that make up matter. These consist of 6 quarks, arranged in pairs to make 3, called generations, identical in all but mass, and 6 leptons, such as electrons and neutrinos. They are arranged similar. There are also a handful of bosons, like the photons, that transmit nature's fundamental forces between the fermions. I'm going to stay completely with my picture. We have here the big whatever cells, the fermions, and in them there are 6. Well, the 6 quarks, the 6 electrons, the 6 neutrinos, and the 6 whatever the other thing, and the bosons are bringing stuff, the natural forces from one to the other. Why not? 2 things, and between them the bosons are bringing the stuff back and forth, so that the fermions are with electromagnetic force, like magnets pulled together. I don't know, but I think it's funny. I don't know what I want to say. And that is now the end of the standard physics. We're going to continue the next part with the standard model part 2. If you're here for the standard model part 2, you can go directly to the next part when we talk about the standard model. Here we're going to do now the lunge training. And if you participate in the lunge training, that is at your own risk. We're bringing the leg up, and we're bringing the foot up and down and up and down and up and down. And we're bringing the other leg up, and we're bringing the foot up and down, up and down and down. Now the legs stand wide apart, and we're breathing in. And out. Again in. Out. And breathing in, close the legs. And out. First exercise, legs wide apart. We're going down into quarter squat, and we're pressing against the upper part of the leg. Only with one hand, but trains the obliques. Now on the other side, just with one hand. We're going down into half squat, and we're pressing again at the middle of the leg. And on the other side. And we're going down into 3/4 squat, and we're pressing close to the knee. They're a bit short on time, so we're going to do all the exercises through in one flow. And on the other leg. And now next exercise, we're pressing against the knee, and we're going towards the knee. Press against the other knee, and go towards it. And again, press against the knee, go towards it. Against the knee, go towards it. Next exercise, full squat, arms to the side. Go over to one side, press against the leg, look up to it, hand, and have a bit of bend in with hand. Up. Over in the middle, to the other side, press against the leg, look up to it, hand. Little bend in with hand. To the middle and up. Now to the lunges. 90-90 lunge. And we're torn up with the back, and we're pressing from the inside against the knee. To the other side. Again, 90-90. And torn up with the back and press from the inside against the knee. And to the next exercise, 90, 135-degree lunge. Torn up with the back and pull the leg up. Over to the other side, 90, 135-degree lunge. Torn up with the back and pull the leg up. Over to the other side, 90, 150-degree lunge, torn up with the back, and now pull at the top of the shin bone. Over to the other side, 90, 150-degree lunge, torn up with the back, and pull at the top of the shin bone. And the last exercise, full lunge, torn up with the back, and pull again at the top of the shin bone. And over to the other side. Full lunge, torn up with the back, and pull at the top of the shin bone. And then the next stretching. The heel onto the ground and pull the toes in. The foot to the left and pull the toes up. Foot to the right and pull the toes up. Foot into the middle and pull the toes up. And move the leg from left to right. Other heel onto the ground and pull the toes in. Foot to the right and pull the toes in. Foot to the left and pull the toes in. To the middle and move the leg from left to right. Closing exercise, legs wide apart, breathing in, coming down, and breathe out. Taking in, out, breathe in, close the legs, and out. I thank you very much, and until the next time.